Hello, everybody, and thank you to the organizers for inviting me and going through all this COVID trouble to organize this. Okay, so I'm going to talk about prime values of polynomials. First, I'm going to begin with the four main problems on primes. So, by the way, I put the notes in the link for the notes I'm going to use in the abstract in the website, if anybody cannot see what I'm writing. Okay, so the first, Landau gave these four problems almost a century ago. So the first problem is Lagrange's conjecture for every positive integer n. There's a prime p between n square and n plus 1 square. The second problem is Goldbach. The third problem he gave was there are infinitely many primes p. P in this talk is always a prime, such that p plus 2 is also a prime. So that's the twin primes. And number 4, there are infinitely many positive integers m, such that m squared plus 1 is a prime. And I guess recently, around 2014, Zhang and Maynard they made important progress in the third one. So you can rephrase. I'm gonna phrase a slightly weaker version of what they proved is that there exists some c positive integer such that there are infinitely many primes p with p plus c also prime. That's one way to phrase. And they said what should be C. And about problem 4, Efthymios worked on it. Well, many people worked on it, but I think the best result for problem 4 is the following by Efthymios 1977. So he proved that there are infinitely many positive integers m such that m squared plus 1 is a prime or a product of two primes. Semi-prime. Okay, and one open question, which initially looks very silly, is this one. Find one quadratic, so there exists an irreducible, sorry, say again? Oh, okay, sorry. Yeah, thank you. Okay, so open question, much weaker than what ideally you'd like to have, but this is still very much open. Find one, so show that there exists. You don't even have to show what it is. So prove that there exists some irreducible quadratic polynomial with integer coefficients that represents infinitely many primes. So such that f of m is prime infinitely often. This is open, completely open. And I guess in this direction, Bayer and Zhao they proved, well, I don't want to go into details, but I'm going to paraphrase what they proved. 100% of admissible polynomial, quadratic, irreducible polynomials f represent at least one prime. So it's much weaker, but it's at least it's for 100%. I'm going to explain what admissible means in a minute. And I should also have said, yeah, I'm so sorry. This open, oh, okay, well, maybe I'll just say it now. Okay, let me write another open question. It somehow compares with the previous open question. So all admissible quadratic irreducible integer polynomials represent a prime. So the second question, you're asking to represent one prime, but you want it for all polynomials. Yeah, and it looks much weaker, but actually this is equivalent to what people call the Schinzel hypothesis for in the quadratic case. Schinzel hypothesis. Yeah, because if you know that every admissible polynomial represents one prime, and you have one irreducible polynomial, f of t, you can also consider f of t plus 1 or f of t plus 2. That's a sequence of polynomials. And therefore, each one, well, a lot of them will have to represent a prime. So the original polynomial f of t represents infinitely many primes. So this is the same as writing represent infinitely many primes. And of course, you can ask, what about higher degrees? Well, all problems in analytic number theory, I guess, they become harder if the sequence is more sparse. So here, the best you can hope is some analogs of these 100% results. So here, Friedlander and Granville. In 1991, they proved the following: fix some positive integer d, then 100% of admissible polynomials t to the d plus a t plus b represent the prime. And this was under GRH. So they vary through all coefficients A and B in a box, and they prove that 100% of them satisfy what you want. In a moment, yeah. Only when I have to. Yeah, in 1 minute. But you know, it's what you saw already in high school, I guess. Okay, Zhu, 2018, There has been a lot of papers after these works, proving 100% Schinzel for some special type of we have a table of all these results in the paper. I'm just going to tell you the last two. So he proved that if you fix the degree, then the polynomial t to the d plus a with probability 1 satisfies Schinzel. And the varying coefficient, the integer is a. And this was proved with a different method next year by Balestrieri and Nick Rome. 2020, I guess. Yeah. Okay, so let me state the Schinzel hypothesis. So it gives you, it tells you what are the admissible polynomials, and then it makes an assumption for how many prime values they get. But the general form is about having actually many polynomials. So for example, if you have the twin primes, you want simultaneously t and t plus 2 to take prime values. So here's the general formulation. Assume that you have n polynomials with integer coefficients. They are all irreducible, and they all have positive leading coefficient. Otherwise, yeah, they cannot even be positive for large values of t. And one more assumption that you need is, yeah, these assumptions are the admissible definition, is that for every prime p, there exists some integer xp such that p does not divide f1 of xp multiplied by fn of xp. And it's the obvious congruence assumption. If you think about it for a second, for what I'm going to write, then there exists some m in n such that every fi of m is prime. I guess the most well-known version is when you ask, there are infinitely many m, such that every fi of m is prime. But as I said before, this is equivalent. And a few comments. Okay, so this version, it generalizes problem 3 and 4 of Landau, so twins and m squared plus 1. And another comment is that it's completely hopeless, and only the case when you have one polynomial, when n equals 1 and the degree is 1, is known. Already 100 years before Schinzel wrote his assumption. That's the Dirichlet theorem for primes in progressions. So all the cases except the simplest are open. Okay, so theorem. From last year, Schinzel holds with probability 1. So we're varying the coefficients of all polynomials of fixed degree, and we prove that 100% of them represent the prime, if they are allowed to do so, so if they are admissible. Yeah, this is not a precise formulation. I'm going to give the precise formulation in a few minutes. First, a bit of notation. Yeah, this is just a small corollary, actually, of the theorem I'm going to write in 5 minutes. Okay, so notation, the von Mangoldt function, if you have a positive integer m, lambda of m is defined, well, if m is a power of a prime, p to the k, then lambda of m is defined as log of the prime. And it's 0 otherwise. You can think of this as being log times the indicator function of the primes. And by the P and T, well, actually the P and T is equivalent to saying that lambda is 1 on average. So typically, it's just 0, but a few times it's not 0, it has a very big value, and that's why the average is 1. Okay, so now I'm going to define the prime counting function, but I'm going to use the von Mangoldt function, psi sub f1 fn. I fix n integer polynomials, and I have a counting function of x. This is defined as follows: for any integer m between 1 and x. Well, it's the counting version of this existence hypothesis up there. I will add basically something like a logarithm. Every time all of these fi of m are primes. So I'm going to take the product of von Mangoldt evaluated at fj of m. Okay, and that's the analog of the psi-Chebyshev function in our setting. And this is a counting function that grows with x, supposedly. And there's a conjecture about how fast it grows. And to state the conjecture, I need to write down the p-adic densities first. So define sigma p for every prime p is some kind of p-adic analog of that. You're counting how many elements t in fp are such that the product f1 of t times fn of t is not 0. And you normalize by whatever you have to, by p. And you need some convergence factors. 1 minus 1 over p to the n. And now I can state the Bateman-Horn conjecture. Sorry? The definition of admissible is, we say that an n-tuple, yes, okay, an n-tuple of integer polynomials, this should say zt to the n. An n-tuple of integer polynomials is called admissible if all of the things before then is satisfied. Sorry. Okay, so the Bateman-Horn conjecture is just a quantitative analog of the Schinzel conjecture, so it tells you how this counting function psi grows. In the context, okay, I'm not going to repeat the admissible definition, but in the context, exactly with the same assumptions as Schinzel's hypothesis, the conjecture states that the limit as x goes to infinity of this psi function, f1, fn of x divided by x, that's the number of terms you have, this should converge, and is just the product of these sigma p densities, an infinite product over primes. That's the conjecture. And it generalizes Schinzel, so let me just remark, it's even more hopeless. And you can view it basically as some kind of prime number theorem, but for twin primes, let's say. If you've never seen any of that, yeah, just think of it in these terms. Okay, and now, yeah, I'm gonna need a big board. None, there is a real density if I don't use von Mangoldt. I have to divide by the product of all the degrees. Yes, there is, but it's one if you use von Mangoldt. Okay, so that's the main analytic theorem in my paper with Alexei. The corollary of which is the previous result I mentioned. Okay, so fix any number n, any number of polynomials, and fix any possible degrees d1, dn. And also fix any constant c that is bigger than n. You'll see later what is c, what's the role of c. Okay, then I will take an average over all polynomials. It's going to be a big sum over all tuplets f1, fn in zt to the n, such that the degree of fi is fixed for every I. It's this prefixed integer di, and such that the coefficients are bounded. So the coefficients of every fi go up to this growing parameter h. So I order all polynomials by the absolute value of the biggest coefficient. And let's say this coefficient is h. And for 100% of them, I will prove that the Bateman-Horn conjecture holds. Okay, so for these, I will add the square of the error term in the Bateman-Horn conjecture. So I will have 1 psi over x, psi f1 fn of x divided by x, minus the product of these p-adic densities when p goes up to log x. Yeah, it's a truncated Euler product. And then I take the square of this error term, and then the statement is that this is O big of h to the d1 plus dn plus n divided by something that goes to infinity, square root log x. The numerator h to this d1, d2, dn is the total number of polynomials that you have. So what you want is, this should be also x squared. Yeah, so you want each of, well, you want these error terms to be a bit smaller than x. And if you, since you have the square, you want something which is little o of x squared. So x squared over squared log x is fine. And then this h to this exponent is, if you think about it for a second, is just how many terms you have in this sum. It's the number of polynomials. And then that's the most important, okay, this is not the most important thing. This is the most important thing. This error term is uniform. So the implied constant only depends on these prefixed values, not on x and h, uniformly in the range where x is between log h to the n and log h to the c. Okay, I guess I should ask if there are questions. No? Okay, so just a little comment. Yeah, this error term, in the applications, you want it to be really independent of x and h, and the important thing is how big you can take x. The bigger x is, then the most prime values a polynomial represents. Because that's the biggest, the range for which this average Bateman-Horn result applies. Okay. So just a few comments. So this means that Bateman-Horn holds 100% of the time in a specific range. Oh, yeah. Thank you. Okay, so first mistake in the main theorem. Totally, yeah. Yeah, this should be maybe with a few extra logs. Yeah, you know, this paper by ENG where it studies average of the Moebius. And yeah, it should be x to the 1/2 plus epsilon in any case. But yeah, it's funny. This paper of Granville and Friedlander, their main takeaway actually was that if you assume GRH, there is also a lack of equidistribution of polynomial values. They proved some kind of analog of this Meyer result about if the congruence is very close to x, then there's not good equidistribution of primes in progressions. They proved some kind of analog that Bateman-Horn actually fails in some specific very large ranges if you assume GRH. Anyway, okay. So nobody really knows what should be the real error term, and there's no good way to do computer experiments, I guess. Okay, so some comments. If you assume GRH, without doing anything smart, just following the proof, you can replace these log h to the c. This is not in the paper. You can replace these log h to the c by something that grows polynomially, x to the 1 over the total degree. So little x can be much larger if you assume GRH. That's the only advantage that GRH would give you. And the other thing is that in this setting where you have totally general polynomials, Filaceta worked on this. Yeah. It's the sum of the degrees, yeah. It's 1 over 2, the sum of the degrees. Yeah, I don't explain it because it's not so important. It's not even in the paper. Okay, so Filaceta, 1988, he proved that with positive probability, a random degree D polynomial represents at least 3 primes, if it's admissible. So he had probability, the exact probability was 1 over D1. And yeah, if the degree becomes bigger, he had only one random polynomial. If the degree becomes bigger, then yeah, this goes to 0. Yeah, and I should also say that this is very important for talk number 2. We have more general versions where you're allowed to impose congruence conditions on the primes that you represent. So for example, you can count how many primes 3 modulo 4 are represented by a polynomial. We have versions of these results in this other setting. Okay, and now I'm going to talk about the proof ideas. The proof ideas of the Bateman-Horn averaged result. Okay, I'm assuming this is not an analytic number theory conference. So let me just start by saying, using this Dirichlet series of von Mangoldt, lambda m over m to the s, this you can write as minus 1 over zeta derivative as the Riemann zeta function times, sorry, zeta s. And then you have zeta derivative of s in the numerator. So this you can verify easily by hand, and therefore you have a convolution identity which states that lambda m, the von Mangoldt function for all integers m, will be this minus this sum over the divisors of m, the sum over all k positive integers that divide m. And I'm going to add Moebius of k times log k. And I should define what is Moebius. Moebius of k is minus 1 to the t or 0 if k is square free and is having t prime factors. And it's 0 if k is not square free, if it's divisible by the square of a prime. Okay, so the main term in everything that we do comes from the small divisors. So the main term, I mean this x, it should be x times this leading constant. So I'm just going to define it. We decompose the von Mangoldt lambda as lambda 1 plus lambda 0. Lambda 1 is minus the sum over all k going up to a small power of m, m to the 0.1, k divides m, and then it's going to be Moebius k log k. And the error term will come from lambda 0, which is minus the sum over the remaining divisors, k bigger than m to the 1 over 10. Okay, and the philosophy is that in this second sum, where k is between a small positive power of m and goes all the way up to m, this is a very big interval. So since you have Moebius, you should get some kind of cancellation. So morally, this will give you the error term due to cancellation in the values of Moebius. So it will be 1 minus 1 for 50% of the time. That's the theory anyway. So just I will only make one comment about how to work with lambda 1. It's kind of easier than working with lambda 0, but it takes way more pages. So I'm not going to tell much about it. So when you work with lambda 1, basically, you can reduce everything to counting solutions of congruencies to very small moduli, of moduli roughly 8 to the 1 over 10 in an interval of the integers, in an interval of length, well, basically 8. 8 is the typical size of the coefficients of the polynomials. So yeah, it's a long calculation to deal with how lambda 1 affects the whole problem, but basically it's easy. And the interesting part is when you handle the error term, the contribution of lambda 0. So I'm going to talk about how lambda 0 affects the problem in the setting where you have one random polynomial. So let's say you average, you sum over all integer polynomials of degree d. D is a fixed integer, and all the coefficients in absolute value of this polynomial f, they go up to h. And then, well, you can think of the contribution of lambda 0 to the whole problem as the square of the sum over all positive m going up to little x of lambda 0 of f of m. Yeah, just replace lambda by lambda 0 in the main theorem. And now if you open up the square, oh, let me just make a quick comment. What do we expect? How do we Well, what's the size we expect for that? Well, lambda should be on average 1, according to the prime number theorem. So the goal should be that this will be lit low of the total number of terms, h to the d plus 1 times x squared. It's the little low of what you would get if you have 1 instead of lambda 0. Okay, and now when you open up the square and you change the order of summation, this will become the sum over all integers k1, k2 of size capital X times h to the d. K1, K2 will just be these values f of m. K1 is f of m1. Okay, so then I'll have lambda 0 of K1, lambda 0 of K2, and then I have this sum over m. Well, I have a sum over m1 and m2 because as I opened up the square, they go up to x. They're positive, and then I have to count for how many polynomials f with integer coefficients and degree equal to d and coefficients of size capital H I have. So how often does f of m1 equal k1 and f of m2 equals k2? So I just freeze the value of f of m1 and f of m2. I didn't do anything else here. And of course, this f of m, it has size, the typical size of the coefficients of f, which is capital H, multiplied by m to the d, because that's a degree d polynomial. And then goes up to x, so this should go up to x to the d. Okay, and then, so now, what is this problem? You're counting degree d polynomials, so you have d plus 1 variables, and you want to solve a system of two equations. K1, K2, M1, and M2 are fixed. So it's basically a 2 by 2 linear system. And as we learn in linear algebra, you have to use the circle method. More precisely, the integral from 0 to 1, e to the 2 pi I f of m1 minus k1 alpha d alpha. This is 1 or 0. I mean, whatever integer I have here, the integral over the unit circle will be detecting whether this integer is 1, is 0 or not. Okay, so that's a circle method identity. I'm going to use this identity to detect whether the value of the polynomial at the first entry m1 equals k1, and also I'm going to have another integral to detect the other equality. And the expression that you get, so this whole thing, I'm just going to call star, the whole line. This will be equal to the sum over all pairs of positive integers, m1, m2, going up to x. And then I'm going to have a double integral over alpha beta in 0, 1 squared, s of alpha, s of beta. I'm going to tell you what these are in a moment. They're exponential sums. And then I'm going to have d plus 1 more exponential sums, the product from j equals 1 up to d of capital D sub h of m1 to the j times alpha plus m2 to the j times beta. And I should tell you what these things are, where s of alpha, alpha is a real number in the 0, 1 interval, is defined as the sum over all integers k of size from 0 up to x times h times x to the d, and then I'll have lambda 0 of k. So this is about the cancellation of the Moebius, and then e to the 2 pi I alpha k. So this is this part here, and this other function, capital D of h, is the Dirichlet sum, is the Dirichlet kernel that we learn about in undergrad course in Fourier analysis. So dh of A is just the sum over all integers k going up to capital H. This has to do with the coefficients being in the same interval, e to the 2 pi I alpha k. There's no coefficient in front, like lambda or Moebius. It's just the exponential. This is called the Dirichlet kernel, and I'm going to do a very precise graph. It's an even function. I mean, it's periodic with period 1. So I'll just plot it for alpha between 0 and 1/2. Well, it's like a delta function. It just vanishes here. But it takes a big value only at the center. Okay, and you have a product of these in this expression above. And what we will use is this theorem by Lebesgue. So remember, everything is about the air term, so we need upper bounds for everything. So he proved that the L1 norm of the Dirichlet kernel is almost bounded. The integral from 0 to 1 of the absolute value dh of alpha d alpha is O big of log h. And let me just briefly talk about bounding the exponential sum capital S that has lambda 0. So there's an easy way to transform S of alpha. Well, remember, S of alpha has this function lambda 0, which is a sum over k dividing m of basically Moebius of k. And there's a way to rewrite S of alpha essentially up to some very tiny error term. It is basically the sum of Moebius k k goes up to x e to the 2 pi I alpha k. All right, and now you have a sum involving Moebius, a multiplicative function and an additive function e to the 2 pi alpha k, and the deep result that we use was proved by Davenport. This result is where everything comes from in our paper, well, in the analytic part. Okay, so Davenport, he proved that the supremum over all alpha in R of the absolute value S of alpha is bounded by h over log h to the n. And that's true for every fixed positive n. Okay, so the trivial bound for this sum would just be h. You just bound both things in absolute value by 1. But he proved that you can even get log h, any big power of log h in the denominator. Okay, so now I'm going to use these things to bound this sum of integrals. This will be the sum over all m1, m2 going up to x. Then I'm going to have the integral over alpha beta in 0, 1 squared. And then the two capital S functions, I will use the Davenport bound. I'm going to get h over log h to the n. N can be anything big and fixed. And it has to be squared. And then I still have this product of d plus 1, sorry, this should say 0, of d plus 1 Dirichlet kernels, and I'm going to bound all except 2 in a trivial way. So what's the trivial bound for this is 2h plus 1. I just bound the exponential by 1. So I'm going to get 8h to the d minus 1. And then I will have the product for j equals 0 and 1 of absolute value d of m1 to the j alpha plus m2 to the j beta d alpha d beta. And now this is a double integral over alpha and beta in the unit interval, and I have two linear functions here of alpha and beta, and if m1 and m2 are different, so the non-diagonal contribution, I can basically replace them by, I can have alpha here and beta. So it's basically like having a product of two Dirichlet kernels. And so if you do some linear change of variables, a two-dimensional change of variables, what you'll end up with is x squared. Okay, this comes from the double sum over m. And then I'll get h to the d plus 1 divided by log h to the 2n. All these h, they come from h squared and h to the d minus 1. And then I'll have the square of the Legendre bound. So it's going to be log h times x to the d. This comes from the Jacobian of the linear change of variables. And it will be squared. So here I used the Lebesgue bound for the L1 norm of the Dirichlet kernel. Okay, and that's the proof. So now use that n is bigger than 2 times d times capital C. And this finishes the proof because remember, you wanted to get something which is little o basically of h to the d plus 1. So if the exponent of the logarithm is big and fixed compared to all of this stuff, then you're fine. Oh yeah, and also you have to use that x only goes up to log h to this prefixed constant capital C. That was in the statement of the theorem. So it's absolutely crucial that x is bounded in terms of the height of the polynomials. And, okay, 3 minutes. So that's the proof of, that's what you do when it comes to the error term. And okay, no more circle method for today, I think. Let me just do a little recap. Okay, so the first thing is we proved for general degree and factorization that Schinzel holds with probability 1. The second point is that we also have quantitative versions, so this Bateman-Horn. And the last point is the proof. It uses 3 elements: second moment calculation, circle method, exponential sums, and the main thing is the averages of Moebius. Yeah, and that's the end of the talk.
Thanks a lot, Efthymios, for this nice talk. Are there any questions?
Yes, we would have to use a slightly more general version of this Davenport result, which exists. It's not clear to me, because you have to work out non-abelian versions of this Davenport result, and I've never seen anything like this. Maybe it is possible, but I think it will be hard, if it is even possible. Yeah, but it's a good idea. Maybe for a PhD student, maybe for Cameron. Yeah. Why are you asking me about the next talk? Ask Alexei, he knows stuff. Yeah.
Vlad, did you have a question?
I think the results will still be the same. Yeah, I mean, I thought about them. Yeah, you can use smooth weights when you're counting, instead of counting polynomials with coefficients in a box, you can use a smooth weight over there. And then the only point is that you can have very good estimates for the analog of the Dirichlet kernel. So Lebesgue gives you some extra log, but you would have O big of 1. And I guess this might be useful if you had harder versions of the von Mangoldt function for which you don't know the Davenport analog. Yeah, I've thought about this, but I couldn't find any applications. But yeah, it's a good question.